got milk, then you're probably pouring it poorly. But there's no point crying over spilled milk when I could teach you how to pour it correctly. You see, you could give a man a glass of milk and he won't waste milk for a day, but you can teach a man how to pour it properly and he will never waste milk again. I can already see all of the keyboard warriors typing away, oh my god, how long is this video? How long is it going to take for you to tell us the actual life hack? I can't believe YouTubers these days are milking everything, every minute of watch time for views. Could you please get a move on? So now my shaken milk has brought all the boys to the yard, I'll give you the TLDW life hack. If you have a milk carton like this, instinctively, you'll probably hold it like this. There's a tall ledge to the milk and you probably don't want to risk it spilling, so you might as well get the opening as close as possible to the glass. And then you pour and everything is ruined. There's just this big glug glug that happens and milk ends up everywhere because it's unpredictable. So the simple life hack, all you need to do is turn the milk around and counterintuitively everything then goes to plan. You know, as long as you pour with a little bit of gumption. So now hopefully your life has changed and your drink pouring skills have been improved for life. But this is Draw Curiosity, and there's nothing more we love here than a deep dive to fully understand a topic. So if you're curious about the surprisingly interesting science behind these Milky Ways, stay with me. So what is going on here? Why does such a small difference in position make such a difference in how the milk stream behaves? And the key is actually what's going on inside the bottle. So to show you all what's happening, I actually went to immense lengths to acquire this extremely hard to find bottle. I searched for hours, I'm not joking, hours on Amazon, which should be a hint that no one wants to sell an improperly designed bottle. But the key thing is transparent. So first of all, thank you so much, Mimo Notebook Bottle, for actually making this video possible. Pouring from the bottom means that the milk covers the opening completely. Whenever milk flows out of the carton, the amount of air inside remains the same because the opening is blocked, but it occupies more space. At the beginning, the air in the carton was at the same pressure as the atmosphere outside, but now it is at a lower pressure. So, as a result, the air outside is pushing against the carton's opening to get in and equalize the pressure differentials. So eventually, the air succeeds, and as it rushes in, it disturbs or even stops the even flow of milk. But wait, there's more! The incoming air forms a bubble as it rises through the milk, until it reaches the layer of air inside the carton. As it pops and the pressure re-equalizes, tiny shock waves are caused throughout the air and milk in the carton, causing the carton to shake. And when these vibrations reach the carton's openings, that also disturbs the even flow of milk. So you get this glugging and the spilling that makes the mess all over the table. But when you pour from the top, it's much less likely that the milk ever completely covers the opening. Therefore, there's always a connection between the air outside and the air inside of the carton, which means that both pockets stay at the same pressure throughout. So in other words, there's basically nothing that will disturb the steady and smooth flow of milk. Unless, of course, you specifically lift the carton at just the right angle so as to cut off the air inside, in which case then yes, you will get the glugging problems as before, but honestly at this point, that's a skill issue. But Inés, I must absolutely always pour my milk in this way. What if it spills? It just feels so secure, I really can't do it another way. Okay, well, we already reviewed this just now. All you have to do to make the glugging glug away is to make sure the pressure of the air inside of the carton is the same as the air outside. And there are other ways to do this. You could poke a hole in the top of the container, and this creates a path between the outside and the inside, so that way both pressures will always be equal. Now, of course, you may understandably not want to turn your carton into Swiss cheese, so if you want to keep using the carton, you could also squeeze the sides as you pour, making sure the air inside the container occupies the same space, even as more and more milk pours out. And this is actually what athletes do when they're running or biking and they want to get water into their mouth smoothly without actually stopping their exercise. And finally, you can just make the carton's opening way bigger, so that way the milk pours out and it doesn't cover the entire hole. And that way, there's always a way for air to flow in and out of the carton, avoiding bubbles and avoiding a shaky stream. But, again, this is a Draw Curiosity video, so it turns out there's a lot more to this than just pouring milk out the wrong way. So I did wonder, if we make the carton hole bigger and milk flows out more smoothly, what happens if we make it smaller? It turns out that if the hole you're pouring through is too small, the milk actually doesn't flow out of the container at all. Squeezing the carton would be the only way to get anything to pour out at all. You may have seen a similar science experiment before where, if you use a thumbtack or a pin to poke a hole in the bottom of a water bottle, nothing comes out. Water only starts leaking out in large quantities if you remove the cap. Now, are milk and water the same? No, but also we're talking physics here, so actually for this explanation, they are. Because in truth, very similar physics are at work here. Surface tension, which I'm sure you've heard of, is responsible for this phenomenon. There are 3 rules to surface tension. 1, do not talk about surface tension. 2, fluids like milk and water prefer shapes that expose the smallest amount of surface area to the air as possible. That means that milk and water pull themselves into roughly sphere-shaped droplets, and it means that when you make a small hole in a bottle, milk doesn't flow out because that would mean exposing much more surface area to the air. And the final rule of surface tension is that it's also very weak and therefore very easily overcome. If you make a bigger hole, the weight of the milk that threatens to pour out is enough to beat the force of surface tension. If you remove the cap of the container or make another hole, the air pressure coming down from above is enough to break the force of surface tension. If you squeeze the carton, you exert force on the walls and the air inside the carton, and that's also enough to overcome the force of surface tension. When a heavier fluid is placed on top of a lighter fluid and allowed to flow, the surface between the 2 fluids becomes very unstable and turbulent as the 2 fluids mix. This is called the Rayleigh-Taylor instability. So what determines the threshold where surface tension is no longer enough to hold the milk in, where air starts flowing in and pushes a dribble or a stream of milk out? As some of you may have realized once I started saying the word fluid, we are going to start considering fluid dynamics for a much more precise explanation. So pop an F for fluid in the chat section because the answer to this question is it's complicated. There are a few factors we also have to consider other than the surface tension of the milk, such as the difference in densities between milk and air and the size and shape of the opening. But what essentially happens when milk starts flowing is that it is energetically favorable for the heavier fluid, milk, to pour down, and for the lighter fluid, air, to fill the space left behind, essentially pouring up. But this doesn't happen all at once. Spikes of either liquid will grow into the space occupied by the other liquid, growing slowly but exponentially into mushroom clouds as the tips of each spike expand outwards due to the differences in pressure at those critical points. Subsequently, curls along the interface between the 2 liquids will form due to differences in density and fluid velocity along that interface. In the end, these spikes, mushrooms, and recognizable features will break up as the 2 fluids mix and dissolve into one another, giving way to chaos and turbulence. And so, in keeping with the milk theme, you can see this effect beautifully when you pour a layer of milk into a cup of tea. Viewed in slow motion, you can actually see the fingers of milk and tea extending out into either direction, and it is then followed by the formation of mushroom clouds, and then, eventually, on a long-term basis, the 2 liquids mix more smoothly. Now, you may have realized that the initial conditions for the Rayleigh-Taylor instability to materialize aren't particularly uncommon at all, so it can certainly be found in a manner of ways in nature. For example, think of any time you may have been swimming underwater. When you're face down, you may have noticed that generally, your nose is pretty comfortable despite being submerged in water. And this is because the Rayleigh-Taylor instability doesn't really apply. The air in your nose, which is a lighter fluid, is above the heavier fluid, the water. So no water gets into your nose unless you're really making an effort to exhale all of the air from your nose outwards. But if, like me, you get curious and you look up to see what the sky looks like from underwater, then suddenly the heavier fluid is above the lighter fluid and all the water plunges into your nose. However, this phenomenon also transcends annoyances of the human experience. We can also see it whenever there's a solar eclipse, so shout out to my recent video about eclipses. When we observe the prominences and coronal mass ejections in the sun's chromosphere, those are where a dense solar prominence overlies a less dense plasma bubble. That's also the Rayleigh-Taylor instability. When shrimp snap their claws underwater and a bubble is produced and it collapses, that's also because of the Rayleigh-Taylor instability. And this is also what is behind the sounds that you can hear whenever you're diving underwater. It also occurs a lot in anything to do with lava, from the simple lava lamp to underground lava systems that occur beneath the Earth's crust, to the expanding smoke clouds from volcanic eruptions. It also happens whenever there are explosions, in general, from the mushroom cloud of an atomic bomb to the shapes of supernovas. So I bet you weren't expecting a life hack video about pouring milk to lead to a phenomenon found all over nature, from shrimp to supernovas. And to be quite honest, when I was planning this video, neither did I. This was supposed to be a quick and easy 3-minute video, and it quickly ballooned and mushroomed out into this. But I think that's the real fun thing about fluid dynamics, is that they're so fundamental. Phenomena like this pop up everywhere, even when you're not looking for them. So the next time you're cooking with chicken broth, or pouring a glass of milk, or making a coffee, look out for all the ways that your liquid stream could writhe and misbehave as it misses your cup and splashes all over your countertop. Or just cut out the fun and pour it the way I taught you. Anyway, as you can see from this video, fluid dynamics is everywhere. And in my view, that is one of the best things about physics. It underpins just about everything we do and experience. And if you want even more insight into the daily phenomena around us, you can learn about it on Brilliant. I've always loved using easily available examples to demonstrate difficult concepts. In some ways, I would say that's maybe one of the most fundamental parts of Draw Curiosity. And Brilliant does this fantastically with its course about scientific thinking. It's split into easily digestible lessons that you can do on your lunch break or on the train home. And you don't even need a computer for it thanks to their mobile app. If you're a visual or tactile learner, each lesson has interactive elements that help you absorb information quickly and test your knowledge at every stage, so you can be sure that you're really learning. And after that, more advanced courses are actually available for you, like their primer on vector calculus, one of the most important concepts anyone needs to gain a deeper understanding of fluid mechanics. The course is challenging, but Brilliant's lessons are a smooth guide throughout the process. And there's no penalty for getting things wrong, and unlike with textbooks or college classes, you can choose to either just skim the surface or go as deep as you like. There's always new content on Brilliant, and that means that there's always more to get curious about. To get started for free for the first 30 days, you can go to brilliant.org/drawcuriosity, or click on the link in the description, and you'll also get 20% off Brilliant's annual premium subscription. And speaking of milk streams, as ever, there will be a Twitch stream going more in depth on the topic of today's video. And as ever, I am so appreciative of all of my patrons and Twitch subs for the immense support in the work I do. And as always, thank you so much for watching me, and I'll see you in the next one.